I'd like to take a moment to help you understand this idea of oscillation, why a limit can fail to exist due to oscillation, and why specifically this graph is doing what it's doing right here close to the origin, bouncing back and forth between positive and negative 1 an infinite number of times, right? This whole idea of oscillation, why that's actually happening. So if I were to go, let's open up Desmos and graph this thing, and just type in the function just like we had it, which was sine. Inside here we want 1 divided by x. Hit enter, and it would be helpful. It'd be totally helpful if you threw in an equal sign. Awesome. All right, so there we have it. Let's collapse all of this. And I'll try to zoom in on a portion of this graph as we get closer and closer to 0. You can see it's starting to look like, the seismograph or even like a barcode or something. It's getting crazier and crazier. I can hit this plus sign and just keep going, right? It never settles down to any particular thing, which is why we say that this limit does not exist due to oscillation. So the question is why is it doing that particular thing? So let me explain it to you thusly. So let's say that I have this function f of x is equal to, let's start with 1 over x. Okay, and so on that particular function, if I were going to graph it, you first learn to graph this thing in algebra 2. You have a vertical asymptote here at the y-axis, and you have a branch of, this is called a hyperbola, actually. You have a branch of the hyperbola over here in quadrant 1, and then you have kind of its symmetric branch over here in quadrant 3, right? Okay. All right, and now let's take a look at another function, and this one maybe we will call g of x equaling sine x, but this time instead of looking at it in terms of the sine function, like the good old sine wave thing, we're going to look at it on the unit circle here. Okay, so maybe I did this one in purple. Look at this, this is beautiful. And I will select a point on here, and it would have an x and a y coordinate, but think of it like this. I'm going to join this to the origin and then bring this segment straight down. And remember that this length of this segment here, this vertical segment, that is the sine value. Right, this one is the sine value there. And what's the input? The input here actually is this angle measurement that's right here. So we'll call this one x, and whatever it outputs here, g of x, is the sine value here. So this one is the x. So really what's happening here is I am generating a new function, and it's a composite function. And this composite function would be equal to, it is g composed with f of x. In other words, it is sine where the input is 1 over x. I first do, remember that with composition, we always do this interior part first. You get an answer, and whatever you get, it becomes the input value for your g of x function. So if I were to select a particular point on this green graph here, and as I get closer and closer to 0, basically the y-axis, what's happening to the value of that point? The value of this point is going to infinity, right? So as we go to the right, in other words, I could use this one-sided limit that we just learned here. So the limit as x approaches 0 from the right of 1 over x is going to positive infinity. And now remember that this becomes our angle measurement for sine. So on this unit circle over here, as my angle gets bigger, it's going to start rotating around the unit circle. And this value here is always the sine value. And it can only ever be in between a positive 1 and a negative 1, right? And as my angle gets bigger, it's going to rotate around here. Here it is at pi. As my angle gets bigger, here it is at, let's say, 3 pi over 2 and 2 pi. And as I wrap around, my sine value is getting bigger and bigger. It's approaching 1, and now it's shrinking down to 0. And now it's getting smaller and smaller down to -1, and then it's getting up to 0. And now it's going to continue doing that over and over again an infinite number of times as this angle value increases over here. Let me show you this on GeoGebra, and this is also on your Canvas page, the same page as, all these video lessons and stuff for the second objective. And I have a GeoGebra sketch. So on this GeoGebra sketch, let me kind of walk you through here. I'm going to first click this on this purple menu bar here, this left arrow to collapse the menu. And this, I need to move this graph screen just a little bit so I can see things happening. And so we have the green graph is 1 over x, f of x equals 1 over x, and then we have the unit circle here. I have a slider that I can control the point A. And remember, the output of that A value, that point here, becomes the angle measurement on the unit circle, and the blue segment there, the length of it is the sine. So watch what happens. I can just click on this one and I can choose to animate this thing. And then watch what will happen to this point B and the length of that segment as that angle gets bigger and bigger. Okay, so I also made it negative, so now it switched directions and now it's going in the opposite direction. Now it's going to come back and it's going to do the same thing as it gets closer and closer to 0. It's going to totally freak out. And again, like if I set this up, if I turn off this animation and move this myself, I put it at small increments, but if I made those increments even smaller, then it would really vibrate or oscillate around that unit circle an infinite number of times, which is where all that oscillation comes from. Okay, so let me just conclude this one last time here. If I go to the very last slide, let me actually escape out of here and go to the last slide and conclude this lesson here by saying that a limit fails to exist. 3 specific reasons. We have differing left-right behavior, we have oscillation, and we have unbounded behavior. And prior to that, we learned how to estimate the value of limits by looking at a graph or looking at a table of values, both graphically and numerically. And what we're trying to do is see if the y values are approaching a unique value L as x approaches A from either side.